starting on time, not Berkeley time? I just had a course that I'm teaching sort of in conjunction with people at Harvard and in Columbia and in BU, and everybody has a different start time. But Berkeley is definitely the latest. Okay, anyway, hi, I'm Shafi Goldwasser. I'm the director here of the Simons Institute, and as you know, we are dedicated to study the theoretical computer science. We have programs every semester, and this semester we have a circuit lower bound program and data science program that are going on, and many of the people here are participants in this program. And we have a beautiful new initiative, which is Journalists in Residence, where we host journalists for one term, who science journalists, who sort of can teach us about how to communicate and can learn from us some things to communicate. Is that a correct assessment of the program? And so far it's been wonderful, and I think that we are only getting better, because this time we have today's speaker, Anil, Ananthaswamy. Am I pronouncing it well? Great. And Anil is an award-winning journalist and former staff writer and deputy news editor for the New Scientist magazine. And he's been a guest editor for the science writing program at the University of California, Santa Cruz. He organizes and teaches an annual science journalism workshop at the National Center for Biological Sciences at Bangalore, India. And he's a freelance feature editor for the Proceedings of the National Academy of Science Front Matter. And he's also written for Nature, National Geographic News, Discover, Nautica, Matter, Wall Street Journal, the UK Literary Review. And we're extremely happy to have him here. And I think you should all, maybe you should, well, they'll see you, I guess, when you get up. You should all feel free to talk to Anil, tell him about your work. And he's a wonderful communicator, and it's such a pleasure to have him here. And he's going to tell us about his new book. Thank you.
Thank you, Shafi, for that introduction. Lovely introduction. Thank you very much. It's a great pleasure to be here. As Shafi said, I'm here as journalist in residence for this semester at the Simons Institute. And this talk is going to be about this book, Through Two Doors at Once. It's a story of quantum mechanics told through the lens of one single experiment. And this book is written for a lay audience, and perforce the talks that I've given on this book have also been for a lay audience, and I suspect this is not the kind of lay audience that has usually been my audience. So I suspect most of you know your quantum mechanics pretty well. But there might be a few people here who may not. So for at least so that I address everyone, I'll keep the level of discussion as if it's for a lay audience. So I hope for those of you for whom this might be old hat, you will bear with me. The thing I really wanted to talk about is how do you tell a story about quantum mechanics given that nothing particularly new has happened in the last few decades that deserves yet another book. So there have been so many books on quantum mechanics, so many popular books. And so the challenge was, well, first of all, why did I even think that it merited a book? And the reason was that I've been a journalist now for about 18 years, writing about physics, quantum mechanics, and a lot of the times you encounter physicists describing some of the counterintuitive things about quantum mechanics, and you're struggling to then try and explain that to your audience, which is a lay reader. And for instance, you hear about things like superposition, quantum superposition. You hear that, quantum systems can be in multiple states at the same time. An electron can be in two positions at once. What does that mean? Or this idea of non-realism. So the idea that the idea that reality doesn't exist until it is observed, or until someone makes an observation. This is the kind of idea that's usually talked about in the popular media quite a lot, about the nature of reality as described by quantum mechanics. This is in direct contrast to the realist theories that we're used to in physics, which is like if you take theories that describe the way our planets move around the sun, those theories are realist theories. The planets exist regardless of whether we observe them or not. We just happen to find them exactly where our theories tell us they will be. which is not quite the same with quantum mechanics. But again, it was hard to understand what all this meant when you're trying to describe it. Or non-locality. Non-locality is the idea that if there is an event in space-time here, then it can influence some other location in space-time, which is quite far away, instantaneously or faster than the speed of light. Now, this is in direct contradiction to the principle of locality, which underlies classical physics. For instance, Einstein's theories of relativity are local theories, which means that no influence can travel faster than the speed of light. But again, quantum mechanics seems to suggest that non-locality is woven into the fabric of the universe, of reality. So all of these concepts were there, and I was struggling to try and figure out how do you tell a lay audience about these things without waving your hands, without just making up words and metaphors, but actually trying to get at what this means in terms of experiments or what the theory is saying. Invariably, the physicists would say, oh, it's all in the math. Well, of course it's in the math, but what does this mean? And that's when it struck me that there was one way into this story, which is to take the example of the double-slit experiment. The double-slit experiment is an experiment that goes back 200 years. And it has been around since then and forms quite the backbone of the kind of experiments that are done in quantum mechanics. So the experiment itself is very straightforward. It's actually so straightforward as to be silly, which is that you take a source of light, shine it at an opaque screen. There are two slits cut into that screen. And the question we have to answer is, what do you expect to see on the other side? Now, this really depends on what you think the nature of light is. And in the 1600s and 1700s, thanks to Newton, we thought that light is made of particles. So Newton had his corpuscular theory of light, corpuscles meaning particles. So if light is made of particles, then our intuition says that this is sort of what we should expect, that the particle should go through one slit or the other slit and pile up behind the two open slits. And, that's that, right? This experiment, of course, was not done in Newton's time. It was done in the early 1800s by a physicist, English physicist named Thomas Young. And when he did the experiment, this is what he saw. He didn't see two strips of light. He saw alternate bands of light and dark. Here, the dark regions represent regions where there's more light falling. So think of that as a photographic plate, and you're seeing a negative. So what you're seeing is an interference pattern. You're seeing alternate bands of light and dark. And this was proof that light acts like a wave. So the wave front of the light hits the two slits. And then from each slit, there's a diffraction pattern. So two new sets of waves start coming out of the two slits. They expand, eventually they interfere, and when they hit the photographic plate, you're seeing the interference pattern. So the places where there's more light, the two sets of waves are lining up crest to crest, and you get constructive interference. And where you're seeing no light, you're basically the crests of one set of waves and the troughs of the other are lining up, and you get destructive interference. So this was fine. The light as a wave idea was around until throughout the 1800s with Faraday and then Maxwell's theory of electromagnetism. All of this went on to sort of bolster this idea that light is a wave, right? And light is indeed an electromagnetic wave. So this was great until quantum mechanics comes along. So early 1900s, Einstein was the first to talk about the idea that light, actually there are certain situations in which light has to be thought of as being made of particles. Quantum mechanics showed us that electromagnetic energy, of which light is an electromagnetic wave, so light is electromagnetic energy, and that all energy comes in quanta. So energy is quantized, so there is a point after which you cannot subdivide energy into any smaller units. So if you take, for instance, red light of one frequency, then there is a smallest quantum of red light. You cannot divide that quantum any further. So this quantum is indivisible, and it's called a photon of red light, right? Now the experiment becomes really interesting. Now, if you think of a, like I think this might, yeah, so this is a red laser pointer. Imagine that this red laser pointer is shooting out one photon at a time. Now, if it was shooting out one photon at a time, you wouldn't see it there. But if imagine if it was, and you were aiming this at the double slit. So now you know that your laser pointer is sending out one photon at a time. You're sending the one photon at the two slits. And now what do you expect to see on the other side? Imagine there's a photographic plate that is slowly collecting these photons one by one. The photons might be coming out one every 10 seconds, one every 100 seconds, doesn't matter. That they're well separated in time. So at any given time, there's only one photon in the apparatus. What do you expect? Again, our classical way of thinking says, oh, if I'm sending particles, one particle at a time, on the other side I'm detecting one particle at a time, surely this is what must happen. The photon should go through one slit or the other slit, and I should see just those two strips of light. Well, this is quantum mechanics, and of course that's not what happens. You get exactly the same interference pattern, except this time the interference pattern builds up over time, right? So previously you had a flashlight or a beam of red laser light, you shone it at the two slits and you got that interference pattern immediately. But now you are exposing this photographic plate to a number of photons, say 100,000 photons that have gone through the double slit apparatus one at a time, 5 seconds apart, 10 seconds apart, and you're still getting an interference pattern. So now the question is, what is interfering, right? Because you know you've sent in one photon, you know you're detecting one photon, so what is it that's interfering? Is the photon going through both slits and interfering with itself? Well, we know a photon, by definition, is an indivisible unit of energy. You can't divide a photon into two. So again, the question comes up, what is interfering? And the other thing that happens is, any given photon out here you cannot predict exactly where it will go on that photographic plate. It will end up in one of those regions that eventually form a band of light. So it will end up in one of those regions of constructive interference. But for any given photon, you can only calculate the probabilities of where it will end up. You can't say exactly where it will go, right? So there is some sort of randomness, indeterminism to this process. I just had lunch with Professor Avi Vidkerson, and he talked about randomness. And I think I realized that my ideas about randomness may be completely off, but I'm going to stick to what I thought I understood. Otherwise, I'll be completely confused. But there is some notion of randomness here. You cannot really predict what exactly each photon will do. Does the photon have a trajectory? Like if I were to throw a ball from here to that end of the room, and I was very precise in how I threw, and if I knew all there was to know about the ball in terms of the forces acting on it, the force of gravity, etc., it would be very easy to predict exactly where that ball will go. Here, you're shooting the photon, you're assuming that you know everything there is to know about the photon, and yet you cannot predict where it will go, which means that you cannot chart a trajectory for it, right? And then what happens if you were to try and see which slit the photon goes through, right? Again, your classical intuition is telling you that the photon has to go through one slit or the other. Let's say you came up with a mechanism whereby you could figure out which slit a photon goes through, right? And if you did that, oddly enough, what will happen is you'll get this pattern back. So if you try to collect which slit information, if you try to collect information about which slit a photon is going through, the interference disappears. If you don't try to see which slit a photon goes through, then the interference appears, right? So this is the essential experiment. And the whole book, I realized that the entire story of quantum mechanics, all of the conceptual difficulties that arise when you look at the fundamentals of the foundations of quantum mechanics can be understood, not answered yet, but understood in terms of this one experiment. So, and this experiment has been done over and over again and built and has become more and more complex over the years. And it provided a perfect avenue for explaining these deep conceptual issues that continue to dog quantum mechanics. So if anyone tells you that quantum mechanics is sorted out, a done deal, don't believe them. It's not. At the conceptual level, it is fabulous at making predictions, probabilistic predictions. It is the most successful physical theory we have. There's no doubt about it. Everything we're doing right now, our computers, all of this works because we understand the world, quantum world, in the way we do with quantum mechanics. But in terms of what it actually tells us about the nature of reality, questions still remain, right? So I thought I'll take this experiment and then start building it up throughout the book. So this became kind of a pedagogical tool. It was a way to tell the story not just of one experiment, but of all the different conceptual issues that really haunt the foundations of quantum mechanics. And if you ever go to a conference on the foundations of quantum mechanics, you'll see what I mean. No one agrees. I mean, there are these distinct camps that are continually at odds with each other. And there is absolutely no agreement as to the nature of reality. By nature of reality, what one means is what is real, what exists. Can we even say anything based on this theory about what exists? All these questions are there, right? So what I did was, in the book, after starting with an introduction that I just gave you about the classical double-slit experiment, I switched to talking about the way this experiment is done in laboratories. So laboratories, they work on optical benches. They use a very particular kind of double-slit experiment. And I just want to run through a few iterations of these slides, because you'll see how simple this experiment is and how many questions you can ask based on this one small tabletop experiment. So this is a source of light which is hitting something called a beam splitter. A beam splitter is simply a half silvered mirror that reflects half the energy of the light falling on it and transmits half the energy of the light. Any window is actually, any pane of glass is a kind of beam splitter, and almost every piece of glass is transmitting some light and reflecting some light. This just happens to be laboratory grade mirror, so it will precisely reflect half the light that's falling on it and transmit half the light, right? Now, if you just again take a regular laser, red laser, and with a strong beam and shine it, half the energy of the laser will go one way, half the energy the other way. Now the same experiment done with single photons. You tune down the laser, or you can't really tune down a laser, but let's say you have some source of single photons that is hitting this beam splitter. And now comes the question, what happens? We know that a photon cannot be divided any further. So it's not like this beam splitter is going to send half the energy of the photon one way and half the other way. That can't happen. What happens if you do this is that the photon is reflected half the time and transmitted half the time. So it becomes a probabilistic thing now. Quantum mechanics tells you that the photon will be in one path 50% of the time and in the other path 50% of the time, right? And we can verify this if you were to put detectors at the end of the two paths, which are photon detectors, and you now send 10,000 photons into this apparatus one by one. On average, D1, the one that is at the end of the reflected path, will click saying, oh, found a photon. And the other half of the time, D2 will click on average. So 10,000 photons, if you send them in one by one into this beam splitter, 5,000 on average will go one way, 5,000 on average go the other way. You can now just change this configuration a little bit. This hasn't changed at all compared to this. All that has happened is the path has been extended. All we have done is put two mirrors at the, at certain points in the path, and they're just deflecting the beam at right angles, and they're still going to those detectors, D1 and D2. So again, same thing. If you send 10,000 photons into this one by one, quantum mechanics says that half of them will go one way, half of them will go the other way, and D1 is going to click 50% of the time, D2 will click 50% of the time. Again, the key here is that any single photon, you cannot say with certainty what it will do. You can only talk in terms of, there's half the chance it'll go one way, half the chance it'll go the other way, right? But on average, it's split into two. Not the photon, but the number of photons. Now you can do something very interesting, which is you put a second beam splitter at exactly the location where the two paths cross, right? So if you go back to the previous one, if D1 clicked, you know that the photon took this path, the reflected path. If D2 clicked, you know that it took the transmitted path. Now, let's say D1 clicked. Is there any way to tell which path it took? It's impossible because the photon could have come this way, or it could have come this way, right? So a photon reaching detector D1 could have been reflected by the first beam splitter and then transmitted next, or transmitted first and reflected next, right? What the amazing thing that happens when you put the second beam splitter into this setup is that now when you send 10,000 photons one by one into this beam splitter, if you try to calculate based on our classical logic as to what happens, it will be wrong. Our classical logic tells you that if 10,000 photons are sent into this setup one by one, then half will go this way, and at the second beam splitter again, half goes this way, half goes this way, and the same thing happens with this path. So basically, in the end, you should end up getting the same averages. You should still get 5,000 going to D1, 5,000 going to D2. This is quantum mechanics. So that's not what happens. Turns out that all the photons, as long as the path lengths are equal, as long as the two paths between the two beam splitters are of equal length, all the photons in this case will go to D1. None will go to D2, right? If I take this out, they split. Half go to D1, half go to D2. You should put the second beam splitter in, all go to D1, none go to D2. And why is that? And this really is, just asking this question why takes us to the heart of quantum mechanics, right? And the reason is because the way the math explains it, and that's where the interesting bit begins. The way the math explains it is, you have to go back to this figure. Let's now think of a single photon going through this setup. The math says that the photon is represented by, the photon has a quantum state. The quantum state is given by what they call a wave function. It's just a mathematical abstraction. And it's the wave function that is made to evolve and go towards the two slits. A wave function is simply, as you all know, it's just a function in space and time. So it tells you something, it has a value at every location in space and time. And that wave function evolves according to something called the Schrodinger's equation, which is just a partial differential equation. I shouldn't say just a partial differential equation, it's quite a profound one. But it evolves according to the Schrodinger equation. So there's it acts like a wave. And so the state of the photon, not the photon, we're just talking of the mathematical abstraction that represents the state of the photon. That abstraction is made to evolve. It hits the two slits, exactly like a wave, diffracts, two sets of waves start coming out from the other side, and they expand and interfere and create an interference pattern. But this interference pattern that's created is of a mathematical abstraction, right? And if you were to say, what does that represent? Well, that's where the mystery is, right? The wave function, if you were to say, what is the value of the wave function the moment it meets the photographic plate at a certain location, you can look at the amplitude of the wave, and when you take the square of the amplitude, you get the probability of finding the photon at that point. It's not telling you the photon is here. It's just giving, so the wave function is now spread out like a wave, and it has different values at different points. And if you take the square of the amplitude of that wave function, the value of it at any given location, you get the probability of finding a photon there if you were to measure, if you were to look for it, right? So which means that the photon could be anywhere where there is a non-zero probability along that plane. And if you were to measure it, it will appear or not appear at the point where you choose to measure it. And the wave function just gives you the probability of finding that. And those probabilities get borne out if you do this experiment over and over again with identically prepared photons with the same quantum state. So if you did 100,000 measurements, just send the photon, it'll turn out that the probabilities that are given to you by the wave function do get manifested in the numbers of photons that land on that photographic plate. Now, if you were to look at this setup now, it's much easier to understand what's happening in terms of the wave function as to why all the photons end up here and none go there. The reason is the wave function of the photon comes into the beam splitter. At this beam splitter, the wave function splits. One component goes this way, one component goes this way. Remember, this is mathematical. We are not saying that something real is going through one path and something real is going through the other path. Mathematically, part of the wave function is going this way, and it comes here, again gets split and goes this way and this way. The other one comes this way, transmitted, hits a second beam splitter, is again transmitted or reflected. So now, if you look at the wave functions that are coming out of the second beam splitter, it turns out that one of the paths has 2 reflections and 2 transmissions, right? So the path that is reaching D2, the wave function could either be reflected and then reflected again, or transmitted and transmitted. So that the wave that is transmitted twice is 180 degrees out of phase with the wave that's reflected twice. So one component of the wave function is lagging the other component of the wave function by 180 degrees. So the crests are lining up with troughs, and you get destructive interference of the wave function. Here, you're getting constructive interference of the wave function because it has 1 reflection, 1 transmission, or 1 transmission and 1 reflection. The waves are in sync, and mathematically the wave functions line up, and you get constructive interference, right? So if you now ask what is the probability of finding the photon here, the wave function's value is 0. Here, if you take the square of the amplitude of the wave function here, you'll get a probability of 1. So in this particular setup, all of the photons go here, none of them go there, right? Now the question is, what is this wave function? Is this real? You know, what just went through both sides? We know that the photon cannot split and go through both paths at once, but something did go through both paths at once, because otherwise how do you explain interference? So these are the kinds of conceptual questions that are very easy to raise with this experiment, and then start talking about how physicists are dealing with it, or what they're trying to, in terms of alternate theories that are trying to address some of these issues that crop up. Let me see. Yeah.
Quick clarifying question.
Yeah.
On that diagram, if you were to take one of the paths in that square circuit and lengthen it by half a wavelength, would that change the situation, and now all the photons would end up in it? It
would. So a phase is basically the path length, right?
Phase is not just because it's reflection versus non-reflection, it also takes the...
It's the length, yeah. So that's why I mentioned earlier that in this particular configuration, when the 2 path lengths are exactly equal, you get constructive interference at D1 and destructive at D2. But you can mess with, for instance, if you put something here that, tuned the path length, varied the path length, from 0 to half a wavelength and back to 0, the counts would keep switching. So yeah, so you could change one of the paths so that all of the photons go to D2 and none go to D1, and anything in between. Yeah, absolutely. In fact, that when they do the experiments, when they're trying to see interference, that's what they're doing. They don't always stick to equal path lengths. They're constantly varying the phase in one of the paths so that you get the counts back and forth, and then you see how it's swinging. So the key thing about this particular configuration, it can be done, as you can see, on an optical bench, and then it allows you to do some really amazing experiments. And one of the things as a writer that you're looking for always when you're trying to tell these stories is you're trying to see where to start, the storytelling. Because now quantum mechanics is, it's a 100-plus-year-old field. There are lots of places in which you can start telling your story. And most of the popular science books tend to start really at the very beginning, because the very beginning is extremely intense and wonderful. We have Einstein and Bohr and all these people arguing, and Heisenberg having sleepless nights and coming up with his matrix mechanics, and Schrödinger really upset at Heisenberg, comes up with wave mechanics. All of these things, they're wonderful stories. They've been told over and over again. Right? So I wanted to find a way in which I could focus the reader's attention on this experiment. What is it about this one experiment that makes you, that you would want to read this particular story, this particular way of looking at quantum mechanics? And again, as a writer and reporter, you're constantly kind of tuned to looking for ways to begin your story, ways to end your story, etc. And it was while I was visiting a researcher at the Perimeter Institute in Ontario, Canada. As usual, as it was with almost all the quantum physicists I met, we would start the discussion and he just jumped up to his blackboard and started drawing equations and diagrams, and I must have looked just as befuddled as I was with each one of them. And he realized, okay, I have to reset this discussion. He said, okay, let me start by telling you something. Imagine there's a factory that makes bombs, right? So as soon as I heard that, I woke up, and then I want to tell you this particular. So this is how the book begins. The book begins by asking the reader to imagine a factory that's making bombs. This is a puzzle that's called the Elitzer-Weidman bomb puzzle, after 2 Israeli physicists who came up with it, and it's quite amazing. So think about a factory that makes bombs with triggers that are so sensitive that even a single particle of light, a single photon of light falling on the trigger will detonate the bomb. The problem is that the factory, which is ostensibly supplying these bombs to whoever wants them, also makes bombs without triggers, the duds, right? And your task is to figure out how to sort the duds from the live bombs. Right? Classically, with classical physics, you can't do this. You have to look at something to figure out whether, and even the act of looking with one photon, doesn't matter whether it's an X-ray photon, if you're trying to do it in the dark, some photon, right? It will explode. So you can't look at the thing. How do you sort out the bad from the good? We're allowed one concession. We are allowed to explode some bombs in the process of trying to at least find a sample of good bombs that can be then shipped, right? And when I was talking to the physicist, his name is Lucian Hardy, he also put the good and bad in quotation marks, saying you might have a different moral perspective, on which I agree with. So this is not to say anything about the morality of these bombs. So how do you start sorting out the good bombs from the bad bombs without looking at them, right? And it can actually be done using this setup, right? It can actually be done using this setup. This is so I didn't tell you why this is a double slit experiment. First, I should mention this. So this particular configuration is a very special case of the double slit experiment. It's picking out, if you go back to this screen here, it's picking out all of those regions on the screen where the phase difference between the wave going from one slit and the other slit is exactly equal, and where it's 180 degrees out of phase. So that kind of represents a one-dimensional view of what's happening on that 2D screen, right? You're picking out all those points. So D1 represents all those points where the phase difference on that screen is 0, and D2 is representing all those points on the screen where the phase difference is 180 degrees, right? So this is a double slit experiment, but a very, very simple, and it's actually very lovely to do on an optical bench. Okay, so we can solve this bomb puzzle using this. And how do you do that? Let me just do one small thing, which is to put a block in one of the paths. Now, when you send 10,000 photons, what happens, oddly, is that only 5,000 get to the second beam splitter. The photons that ostensibly are going through this path get blocked. So only 5,000 make it here, but of the 5,000 that make it here, remember, without this block, all of them would have gone to D1. But with this block now, the 5,000 that come here, half go to D2, half go to D1. And the reason is that you have to think of it, you have to think again of wave functions. The wave function is going like that, and that gets blocked. It doesn't go any further. This component of the wave function goes all the way here, doesn't meet anything else to interfere with, and half of it goes this way, half of it goes this way. So essentially, you ended up with a wave function with half the amplitude going this way, half going this way, and so the probabilities are 50-50, but of the 10,000 photons you sent in here, 5,000 got blocked. Of the 5,000 that went this way, you got 50-50 split. So in this weird configuration with one arm blocked, you will see some photons ending up at D2. If this wasn't there, there will be no photon at D2, right? So now we can tackle the bomb puzzle. Now, imagine this is a bomb placed right next to the interferometer arm. It has no trigger. This is one of the duds, right? So and our task is to find live bombs without triggers, without looking at them. So now if you send 10,000 photons into this beam splitter, it's no different. I mean, there's nothing obstructing the path. The bomb doesn't have a trigger. So all the photons should go to D1, right? So if you place one of these bombs, let's say you're doing this in a dark room with robots, so you can handle them and they don't explode for some reason. So you can put one next to the interferometer like this. So this is called this setup is called a Mach-Zehnder interferometer. So now if you send a million photons and all of them end up at D1, it's very, very likely that the bomb you place next to the interferometer is a dud, right? But if you had a bomb with a trigger, which was obstructing the path, one of the paths, now something very interesting happens. This is acting like a detector. It's acting like the block you put into one of the paths. right? Half the time the photon is going to take this path, it's going to meet the bomb, the trigger, and the whole thing will explode. You reconstruct your interferometer, start all over again, right? And let's assume that each time it goes this way, you're going to blow it up. But half the time the photon is going to take this path. And it's going to come here, and then half the time it's going to go to D1. That's inconclusive. D1 could also happen if there's a dud. But if the photon goes this way, which it will because there is no interference happening, this path is blocked by the bomb, you will get some photons going to D2. And the moment a photon goes to D2, you know there is a live bomb here with a trigger obstructing your interferometer, but you have not interacted with it. Because if you had interacted with it, it would have blown up, right? So this raises a profound question. You know, you have knowledge about something without having interacted with it. What interacted with it? Some quantum physicists will argue it's the wave function that interacted with it. This is proof that the wave function is real, right? This is not a resolved debate about the status of the wave function. Is the wave function something real in the world, or is it just a mathematical abstraction that we use to understand how quantum systems behave? This is something called interaction-free measurement. And if this all seems like a little, esoteric, as if, oh, this is just well, this was a thought experiment, but these experiments have been done with photons in the lab with specialized configurations, and this has been tested. This happens, right? So another
clarifying question.
Yeah.
On the nature of that trigger.
Yeah.
So we have to make quite clear that the dot does not have any trigger at all. It's not like it has a trigger, but the electrical wire from that trigger to the bomb.
Yes, it's a physical obstruction. Yeah, I should have made that clear. So the dud is simply a bomb without a trigger. If it has a trigger, it's an extremely sensitive trigger. Yeah. So, and of course, you're placing it so that, it exactly obstructs the path, right? And it's a photon, so, this is all thought experiment, so bear with me. But the point to be made here is that this configuration of a double-slit experiment actually picks out something without interacting with it, right? So this becomes a way of understanding, or at least raising the question about the status of the wave function. What is the wave function, right? So you can see that the double-slit experiment, even the very minimal stuff that I've shown you, already allows you as a pedagogical tool.
Well, okay. We've now used the term real several times.
Yes.
And I've always been curious about what do these physicists mean when they say this is real, this is merely a mathematical abstraction.
So in this way, the way I'm using it is it's basically the kind of debate that Einstein was having with Bohr about realism. So to Einstein, a physical theory should be capturing the real world, which exists independent of you or I or any observation looking for it. It's just there, and our physical theories are capturing that reality. So there should be variables in the theory that tell us what's out there, right? Whereas, so real in that context. So something that's real independent of an observer or an observation, and we just discover what's out there. Right? Yeah.
However, on that note, I seem to discover a certain bias. When you talk about the photon as a particle, then you sort of imply that's real. When you talk about it as the wave bundle, then that's the mathematical abstraction. But you could turn this around.
You can. And the photon, the photon is a quantum system. It's described by a quantum state, and a quantum state, and that's where we get down to this issue of, is the quantum state describing something real? So in quantum mechanics, there is no way to describe the trajectory of a photon as it goes from here to there. There is no variable. There are no sets of variables that capture the position and momentum at every point as the photon travels from here to there, right? You can't do that. It has a position only upon observation. So it becomes real, so to say, upon observation. It has a definite position the moment it's observed, but until it's observed, you can only talk probabilistically about where it might be. So I'm talking about realism in that context. Is the theory capturing something that... So if you interpret standard quantum mechanics, so standard quantum mechanics is basically a lot of lovely mathematics that allows you to make predictions about the outcomes of experiments you might do. And these predictions happen to be probabilistic, and they're very accurate and all of that. But then you start interpreting as to what the mathematics says. and the Copenhagen interpretation, which is kind of a loose name for a whole bunch of different things. And one of the things that the Copenhagen interpretation will say is that you can't talk of the photon as being real until you've observed it. So in that sense, it's an anti-realist interpretation. But again, it's very divisive, the field. Not everyone will agree that that's what the Copenhagen interpretation says. So these debates go on and on and on. No one's quite sure what Bohr was saying anyway all the time. So it's very hard to kind of pin down any one person's philosophy on this. But my point in the book was to make it clear to the reader that, look, these distinctions are there, we don't understand them, and these are the tools to understand the philosophical debates, not answer them, because the debates have not been resolved yet, right? So, and for the issue of quantum superposition, right, I brought this up earlier. What is quantum superposition? It's a weird thing. All we are saying is that the wave function exists in, it takes both paths. And that seems to imply that the photon exists in the superposition of going through one path and the other path. But is it really going through both paths? Not really. Is it going through one path and not the other? Not really. Is it going through neither? Not really. We really don't know. That's the whole essence of it. We can't say anything about what the photon exactly is doing, given the mathematics, right? Now, someone like Einstein will say, well, that's because the mathematics is incomplete, that there have to be other variables that capture what the photon is doing, and we just don't have them, and there is a hidden reality that needs to be captured by the mathematics, and there have been attempts to do so, right? So the point I'm trying to make here is that just this simple experiment allows you to understand what physicists are saying when they say, oh, the photon is in a quantum superposition of taking both paths. It's a mathematical way of saying the wave function splits and goes two ways, but that's not the same as saying the photon is going through both paths. Complementarity and wave-particle duality. This was Niels Bohr's idea that nature has particle nature or reality has particle nature and wave nature, and you can only observe one or the other, and what you observe depends on what you're looking to see. So if your experiment is designed, if your experiment is designed to look for the particle nature, which this configuration of the interferometer without the second beam splitter is doing, then you will see the particle nature, which is half of them go one way, half of them. So you can talk of the photon taking one path or the other path. You can talk of it as a particle. But if you put the second beam splitter in, this entire configuration now is looking for its wave nature, and you will see its wave nature, and you can't, one is to the exclusion of the other. This is now again debated. There are experiments which are showing you can see 30% wave, 70% particle. It gets very, very hairy, but the point is that, again, you can look at this simple experiment and understand what somebody like Bohr was going on about. And determinism versus non-determinism. This probably has become clear to you by now, that you can only talk of things happening at the quantum level in probabilistic terms. You can't so the outcome of an experiment, you can only assign probabilities to the outcome. You cannot deterministically say exactly what's going to happen, right? There might be multiple outcomes for the same thing, and they will all have different probabilities. So any given instance of that experiment, you will see one of those outcomes. You cannot deterministically say exactly what will happen. The probabilities get borne out when you do the same experiment a number of times. So again, all of these conceptual issues can be understood. The biggest thing that this throws up is something called the measurement problem, which has to do with the collapse of the wave function. And let me, for this, go back to that this figure here. So if you think of this wave that's being represented here, not as the wave of light, but the wave function that has gone through both slits, and it has expanded on the other side, interfered, and it hits the photographic plate, then at the photographic plate, standard quantum mechanics says that it's the act of measurement that causes the collapse of the wave function, because at the plane of the photographic plate, the wave function is spread out, which means that if you were to calculate the probabilities of where you might find the photon, you will have non-zero probabilities in many places. All of those places which represent constructive interference, there will be non-zero probabilities, right? But then the wave function encounters the photographic plate, and standard quantum mechanics says that the act of measuring, the act of observation, is the thing that collapses the wave function such that it goes from being spread out to being peaked or localized. The photon appears in one place. It could have appeared in any one of those places where the probability was non-zero, but it appears at one place, right? Now, this kind of language has been used to argue that the observer is central to quantum mechanics, right? But is it really, right? This is so. The language has been used to say that the measurement, the observer, causes the collapse of the wave function. The mathematics does not define anywhere what a measurement is, right? The Copenhagen interpretation simply divides the world into quantum and classical, and the classical world is the one making the observation on the quantum world, but it doesn't say what a classical world is. It doesn't say where is the transition from the quantum to the classical. How big does the measuring device have to be in order for it to collapse the wave function, right? None of those things are there in the math. There's just some by diktat that it's said, oh, there's the quantum system and there's the measuring apparatus. The measuring apparatus collapses the wave function, right? Given that it's not there, when you kind of run this argument through in your head, you end up with things like Schrodinger's cat being dead and alive at the same time, etc., etc. And it has often been used to argue for the primacy of human consciousness as a way of collapsing the wave function. But the point I made in the book is that the experiment and the math actually says nothing about human consciousness, right? Those are just things we make up. And it actually becomes fodder for talking about quantum mechanics in odd ways. And the reality is that the math is just making probabilistic predictions about the outcomes of experiments, and then there are interpretations. There is a central axiom in quantum mechanics which says measurements causes collapse, but it doesn't define what a measurement is. So for a lot of people working in the foundations of quantum mechanics, this is a huge issue, and it's called the measurement problem. It's related to the collapse of the wave function. So a lot of the other alternative interpretations and alternative theories that are trying to solve this measurement problem, and by solving the measurement problem, the idea is to come up with a theory that does not depend on a measurement for the wave function to collapse. It does not depend on an observer, right? Can it be something that happens and we as observers, as measuring devices, just discover what has happened? And so those alternative theories exist. There are other questions that come up. Realism versus non-realism, we've been discussing it. So there are theories. You can argue that standard quantum mechanics is non-realistic. You know, that's an extreme interpretation, but there are people who will say that. There are realistic versions of quantum mechanics. You can't call it quantum mechanics, but I'll mention it in a bit. But there are other alternative theories that are realist, that says, for instance, that a photon exists at all times, and it has a definite position, and it's a particle with a definite position and momentum at all times, and that's a realist theory, unlike standard quantum mechanics. The wave function, questions about the wave function come up, which you can ask in the context of the double-slit experiment. Is it epistemic, in the sense that is it just representing our knowledge about the quantum world, or is it ontological or ontic? Is it actually something real? If it is something real, then it's quite a bizarre thing, because the wave function moves not in three-dimensional space, but in a multi-dimensional configuration space. So if there are n particles, then the dimensionality of the configuration space is 3 times n. So it's a massively, so if you take 10 to the, I don't know how many particles there are in the universe, so the wave function for that would be in some really, really massively hyperdimensional space. So it's moving around in this mathematical space, and its value is a complex number. So what on earth is real about it? We have no idea. But there are very, very strong arguments to be made about the wave function being something real. If it is something real, then it leads to other issues, like entanglement and non-locality. Like if the wave function is something real and it has spread out, and you make a measurement, and the wave function collapses at one point, its value peaks at one point, then Einstein was the first to point out the problem with this, is that the moment it peaks at one point, and if you consider this wave function to be real, then it has disappeared from all other points in space-time. And this wave function could have been spread out as much as you want, and one act of measurement at one point collapses it, and it's disappeared in value. Its value has gone to 0 everywhere else. That's a very non-local behavior. There's a notion of simultaneity built into the collapse, which completely contradicts special relativity. There is no notion of simultaneity in special relativity. So you can see why Einstein was so terribly bothered by this, right? But so you can start explaining notions of entanglement, of non-locality, using this one experiment. You can also talk about the various interpretations. Copenhagen, I mentioned that so far. There's probably the strongest alternative to that. Well, I shouldn't say strongest because depending on who you talk to, they'll disagree or agree. But there's de Broglie-Bohm's theory, which says that nature is both wave and particle. And the simplest way to understand this in the context of the double slit is you shoot a photon at the double slit. It will go as a single particle through one slit or the other, but it's being guided by a pilot wave. The pilot wave is the one that hits both slits, interferes on the other side, and then guides the particle to one of the places of constructive interference. So nature is both particle and wave, and in this case, the wave function is real, except that it moves around in this weird configuration space, right? And the particle is real. So this is a realist theory. It's also deterministic, but it's extremely non-local because there is only one wave function and all particles are interacting with this wave function. So anytime the wave function changes, all the particles in the universe are instantaneously affected by it. So something you do here could affect a particle on Andromeda instantly, according to the theory, right? So you can see why that can create other kinds of problems. But that's a very formidable sort of alternative to standard quantum theory. There are so-called collapse theories. Collapse theories are basically, remember that the big conceptual problem with standard quantum mechanics is the notion of collapse. Like, what causes collapse? Why should we make measurement the centerpiece of the theory, even when you can't even define what a measurement is? So collapse theories are basically saying that collapse happens stochastically. It happens randomly throughout, so if there's a wave function, it's almost like multiplying this wave function with something that is peaked at one point, and it ends up collapsing to that location, at that location, but that is random. And the mathematics has built into it the properties that it needs in order to replicate the empirical data that we have from experiments. So it will replicate exactly the predictions of standard quantum mechanics, except that it is not dependent on the observer and the wave function is real. So all these things are slightly different, right? There's of course the many worlds interpretation, which boggles your mind in other ways. So what this says is that when the wave function splits and goes through two slits, and if these two wave functions are not brought back again to interfere, they eventually will interact with their individual environments and they will become what's called decoherent. They can't interfere any further. Once they can't interfere any further, they are in separate universes. So each time you split the wave function so that, and they decohere to the point that they can't be made to interfere again, you are now in separate universes. So every time a wave function, and if you think this makes no sense, there is actually a company in Geneva that will split the universe for you. So if you have an iPhone, you can download an app called the Universe Splitter. And if you have a decision to make, say, should I do this or shouldn't I do this? Just ask the Universe Splitter. It sends a command to Geneva. All that thing in Geneva does, it sends a photon through a beam splitter, and it'll send you back the reply saying your photon went through this arm of the. Right? And you can see in your app saying, okay, do whatever you choose to do, except that in another universe you've got the opposite answer, so you can rest easy that in another universe you've done the other thing, right? So there's also something called quantum Bayesianism, which is quite interesting in the sense that it's a very small coterie of people pursuing it, but the idea there is that the wave function that we've been talking about, until now the wave function has been ascribed to the particle. Right? It's basically, we're saying that the wave function describes the quantum state of an electron or some quantum system. In quantum Bayesianism, the wave function is simply in your head. It has nothing to do with the real world. Make of that what you may, but it has its own logic behind it, and it works in certain ways. It's still being worked out. But so these are kind of the major categories of interpretations that are trying to solve essentially the measurement problem, the collapse problem, right? And trying to come up with theories that are saying something about what's out there and not just being an instrumentalist tool to make predictions about outcomes of experiments. So you can see how one single experiment can take you through the entire length and breadth of quantum mechanics. And that's what sort of I ended up doing in that book. Yeah. Well, thank you very much. Happy to take questions. Yes, Mark.
So I'll start question from the beginning. You said that there's been very little in the last few decades which have been sort of radically changed. Quantum physics, but for many of us in this room, quantum computing was a very big development. Question about what...
Yeah, so I was thinking more in terms of the foundations of quantum mechanics, and conceptually as anything. So quantum computation, I would argue that is using standard quantum mechanics and taking it in a certain direction. But in terms of actually understanding what quantum theory is saying about reality, that nothing. So the big thing that has changed is probably all of the experiments that were done to test non-locality. So all the Bell's tests.
I was more wondering about, you were also trying to reach an audience, and many more people could probably be reached by alluding to this connection to the...
I would agree, yes, yeah. I kept away from that because this was a very focused book on the experiment. But yeah, I would very much agree with you that quantum computation it raises actually very profound questions about exactly these things, because now you're using these conceptual ideas that come from standard quantum mechanics with the sort of instrumentalist approach and are able to do these things. And that's suggesting that some of these things that are being claimed by standard quantum mechanics are actually happening. And I don't know how to analyze that from the point of view of quantum computation, but certainly, yes, that would be a great way to get more people involved.
I would just add to that. I think it proves definitely the foundations of quantum mechanics. You didn't talk about multi-particle systems. You talked about one photon.
Yeah.
Quantum mechanics talks about, or at least makes claims about multi-particle systems and entanglement between them. These are foundational issues.
Right.
Even the mathematics, not just the interpretation of mathematics,
So
is not clear when you think about quantum mechanical algorithms.
So in this particular case, what I didn't, so in the book I talk about multi-particle entanglement. Remember, I mentioned somewhere in the middle that if you had a way in which you could figure out which slit a particle is going through without destroying it, if you just collected information about which slit a particle is going through, then you could potentially, you would essentially mess up the interference pattern. But how do you do it? With a photon, you can't measure it to see which slit it's going through without destroying it. And the way you do it is by using entangled pairs of photons. So you send one of the entangled pair into the beam splitter, and the beam splitter is designed, it's called a polarizing beam splitter, where if the photon is horizontally polarized, it takes one path. If it's vertically polarized, it takes another path, right? And you have the other photon with you, which is now entangled with the photon that went into the beam splitter. So if you did a polarization measurement on the pair that you have, you would instantly know what happened to the other one. So if you make measurements on the entangled partner, say in the horizontal basis, and found it to be horizontal, then you know that the photon that went into the beam splitter took one path and not the other. But if you made a measurement in this is getting into kind of details about polarization measurements, but if you were to measure the polarization of the entangled partner that you have in a way where you can't tell whether it's horizontal or vertical, then you kind of erase that information that you had, and the photon that goes through the beam splitter will act like a wave. It'll interfere. So yeah, I mean, and in order to understand entanglement, you have to talk about the very first Bell experiment and all that. So which I do in the book. It's basically set up to talk about multiparticle entanglement.
Yeah, so I've been worrying about these kind of issues for almost 60 years now. So I'm bold enough to offer another interpretation philosophy, which has sort of kept me sane in the wealth of possible different interpretations. I think it all started when, as a high school student, I read that Heisenberg said, the kind of answers you get from experiments depends on what questions you ask. If you ask a photon, are you a particle? The photon says, yeah, sometimes I behave like a particle. And if you ask the photon, are you a wave? He says, yeah, sometimes I behave like a wave. So since then, I have sort of scaled back, and I don't think that scientists really are out there to get the truth and find out what's real. What scientists do is they make a model of what they think describes that very, very complicated world out there. And you judge a model by how simple it is primarily, and then how much predictive power it has. And that gets rid of a lot of these kind of fuzzy instances, because let's assume that a photon is something much, much more complicated than either a wave or a particle, whatever. Maybe some wave-like thing that spreads through the whole universe and indeed has all of that. Then our quantum mechanical wave function becomes a very, very simplistic abstraction of something like that. And it basically tells us what we know about the photon. And we suddenly know exactly where the photon is, and the wave function collapses. Well, that's our primitive model. It doesn't mean that that's what's really happening in the universe. And so,
yeah. So you are
reality and your best model that you can think of. Some of these deep philosophical problems sort of go away.
True. So the instrumentalist would argue exactly like you're arguing, that they would say that let's just, in fact, that's how quantum mechanics is practiced without worrying about these physical, interpretations of what's happening at the level of physical reality, right? Certainly. But there have been physicists, including Einstein, who wasn't happy with that. His point was that our theories in physics should be actually about understanding what is real. And we still don't quite know when it comes to quantum reality what to make of what the theory is saying about the nature of reality. And you can find enough people who will take that position, even now. And all of the alternative approaches are about that. You're very right that, that's one way in which you can just, so say those philosophical issues go away. Because quantum mechanics is a fabulously successful theory. Right? I forget the decimal digits to which it has been verified, but I think, there are things that have been verified to 14 decimal digits. It's really the most accurate theory out there, but it still doesn't tell us, for those people who really worry about this, and there are physicists who worry about this, it still doesn't tell us about what really is real. And even that, I'm putting that in quotes because there's argument about what that even means. Right. Yes, sir.
Yeah, I'm just wondering whether you say that something as classical as time is real.
Time, I don't even want to go anywhere near time.
It's way before quantum mechanics and every physical theory has time. It's also the classical one.
Well, quantum mechanics, standard quantum mechanics, time flows one way. And there are time symmetric formulations of quantum mechanics.
If it's real. I know about this deeper issue. Just is it real?
I don't deal with it in this book at all. The only place where I point out is this, the only place where I point out the notion of time getting us into trouble is with this configuration. So this is, if you switch between these two configurations, you get to do what's called Wheeler's delayed choice experiment, right? So, are we running out of time? Oh my God, 3:30. So I'm happy to stop or go on. Shall I talk about this one little thing? Okay. I didn't even see the clock. So this is a Mach-Zehnder interferometer where you are choosing to see the wave nature. This is the configuration where you're choosing to see the particle nature, right? So what John Wheeler suggested, that what if we let the photon enter the setup without the second beam splitter in place, let it enter. Now, if you're saying that the photon has some intrinsic nature, right? Its intrinsic nature in this case should be, let's say, that of a particle. It's going to go in one path or the other path. And then just before it hits that intersection, you somehow insert the second beam splitter, right? Now what's the photon to do, right? It turns out it acts like a wave because it encounters the second beam. But then just before it encountered that, you were ascribing to the photon an intrinsic nature, which means it has to go back in time and undo its intrinsic nature and come back into the apparatus as a wave. So when you start thinking in terms of time, this really messes you up. Or if you think in terms of the photon having an intrinsic reality before you detect it, right? So time becomes a messy issue here. I stayed away from time entirely in this book. Well, thank you guys. Thank you very much.